If we observe the stars on the sky in a clear night, we will see that they have different brightness and colors. A nice example are the stars forming the Orion constellation. Betelgeuse, located at the top left of the constellation, has a distinctly red color. On the other hand, Rigel at the bottom right has a very blue color. The different colors of the stars reflect the temperature at their outer layers. A star forms when a cloud of interstellar gas collapses under its own gravity. The compression of the gas during the collapse results in the dramatic increase of the density and temperature in its center. When the temperature at the center of the collapsing cloud exceeds a few million degrees, hydrogen atoms start to fuse into helium atoms, producing large amounts of energy. At this point, the collapse stops, and we have a newborn star. The produced energy increases the pressure at the interior of the cloud, which counterbalances the force of gravity that drives the collapse of the cloud. At this point, we say that the newborn star is in hydrostatic equilibrium, meaning that its internal pressure equals its gravity. Therefore, a star is a spherical concentration of gas, with high enough temperature and pressure at its center to sustain nuclear fusion reactions, which produce enough energy to be in hydrostatic equilibrium. The source of the vast amounts of energy produced in stars was one of the biggest puzzles in astrophysics. In 1920, the British astronomer Arthur Eddington, based on the advances in physics, proposed nuclear fusion as the key mechanism.
The amount of energy required to sustain this gravity-pressure balance increases with the mass of the star. A star like our Sun produces 380 septillion watts of energy. This is 38 followed by 25 zeros. To do this, it uses about 600 million tons of hydrogen every second, which are transformed to helium. Using Einstein's famous equation E equals mc squared, we find that the produced energy corresponds to the conversion of 4 million tons of matter into energy every second.
More massive stars have stronger gravity, and as a result, they need to produce more energy in order to remain in hydrostatic equilibrium. Therefore, stars more massive than our Sun are more luminous and hotter. If we plot the luminosity of the stars against their temperature, we find that their vast majority occupy a narrow stripe. This diagram is known as the Hertzsprung-Russell diagram, or HR diagram, after Edsnar Hertzsprung and Henry Norris Russell, who independently created it around 1910. As we see, most of the stars form a rather narrow stripe that goes from high luminosity and high temperature at the top left to lower luminosity and temperature at the bottom right. This stripe is called the main sequence. It is interesting to note that while the temperature changes by only a factor of 10, the luminosity changes by over 10 million, from the most luminous hottest stars to the least luminous and coolest stars. The driving factor for these dramatic changes is the mass of the stars. Massive stars with mass more than 30 times the mass of the Sun are located at the top left of the main sequence. In contrast, stars at the bottom right of the diagram have mass as low as 1/10 the mass of the Sun. But how does all this have to do with the appearance of stars? The light we observe comes from a rather thin layer at the outer parts of the star called the photosphere. This is the deepest part of the star that we can observe directly. The photons produced from the fusion reactions at the center of the stars are continuously absorbed, re-emitted, and scattered following a random path towards the photosphere. This process is what prevents us from observing the inner parts of the star. In the case of the Sun, a photon produced at its center can take more than 100,000 years to emerge. The radiation emerging from a star bears the imprint of this continuous interaction of the photons with the material of the star. This imprint is observed in the form of spectral absorption lines. The intensity of the different absorption lines gives us information on the composition and temperature of the material in the stellar photosphere.
Because a star is in hydrostatic equilibrium, the temperature of the photosphere is a function of its radius and luminosity, which in turn are driven by its mass and evolutionary state. The first systematic exploration of the differences in the radiation that is emitted from the different stars was performed at the Harvard College Observatory in the early 20th century.
This painstaking work was led by Annie Jump Cannon, one of the first women astronomers. She is recognized as the architect of the stellar classification scheme we still use today. Her scheme was based on the relative intensity of different spectral lines, which as we saw reflect the temperature in the stellar atmosphere. Hot stars at the top right of the main sequence have spectra with strong helium absorption lines in the optical spectra, indicating very high temperatures. Stars with lower temperature and mass show stronger hydrogen lines with no helium lines, since they do not produce photons energetic enough to ionize and excite helium. Cooler stars with mass similar or lower than the Sun show increasingly stronger lines from other elements like iron, magnesium, sodium, or even molecules. A star spends most of its life at the main sequence, where it transforms hydrogen to helium. Since massive stars need to produce more energy to survive, they consume their available hydrogen faster and their lifetimes are shorter. Exactly because massive stars produce larger amounts of energy, they have higher luminosity and higher temperature, explaining their location at the HR diagram. A star that is 10 times more massive than our Sun lives only about 32 million years. In contrast, our Sun is 4.6 billion years old and is expected to stay in the main sequence for about another 5 billion years. But what happens when a star exhausts the available hydrogen in its nucleus? Then there is not enough material to sustain the nuclear reactions, and the star starts to shrink under its own gravity, resulting to a hotter and denser core. At these conditions, the elements produced in the previous stages in the evolution of the stars can now fuse, producing even heavier elements and energy. The exact set of reactions that take place depend on the temperature and the density of the star, which are determined by its mass. As a result, the star becomes more luminous while its outer layers expand and get cooler. At this point, the stars move away from the main sequence and to its right. In the case of massive stars, these are the supergiants like Betelgeuse, which is about 17 times more massive than the Sun. In the case of stars up to a few times the mass of the Sun, these are the red giants. However, every star will reach a point when the condition in its core cannot further sustain fusion reactions. In the case of stars more massive than 10 solar masses, this point is when iron and nickel form, creating an onion-like core with increasingly heavier elements in its center. In the case of a star like the Sun, this happens when the core is mostly carbon and oxygen. What will happen next depends again on the mass of the star. Stars less massive than about 8 times the mass of the Sun, shortly before reaching this stage, would have expelled their outer layers, leaving a naked, very hot core. Its temperature can reach up to 100,000 degrees, and they have very high density. They have mass similar to that of the Sun, in a radius similar to Earth's radius. Since this core is not producing energy, it is slowly cooling down, radiating away its heat. This is a white dwarf. In the HR diagram, white dwarfs are located at the bottom left because of the very high temperatures and low luminosities.
However, The core of stars with mass more than about 8 times the mass of the Sun is so massive that its internal pressure is not enough to support it. As a result, it collapses under its own gravity. The vast amounts of energy produced in the collapse power the majestic explosions known as supernovae. Although most of the produced energy escapes as invisible neutrinos, supernovae can be several billion times more luminous than the Sun. In fact, they are so luminous that they can be seen in other galaxies at cosmological distances.
The most recent supernova in our neighborhood was observed on the 23rd of February, 1987. It was produced by an evolved supergiant star about 20 times more massive than the Sun, in our closest galaxy, the Large Magellanic Cloud. But what happens to the material lost from the star in the final stages of its life? In the case of low-mass stars, it will form a cell-like nebula around the white dwarf, called the Planetary nebula. They are usually spherical and sometimes they consist of multiple cells, reflecting different episodes of expulsions of the stellar material before leaving its naked core. Similarly, the explosion of a supernova leaves behind a spherical cell, called a supernova remnant. This cell expands supersonically into the surrounding interstellar space, and it can be visible for several thousand years after the explosion. The energy of the shock wave hits the material it interacts with. The inner part of a young supernova remnant is filled with million-degrees plasma visible in the X-ray band, but invisible in the optical. As the supernova becomes older, the X-ray emission fades away, while the outer shell will eventually become so diffuse that it will merge with the interstellar space. Both planetary nebulae and supernovae are extremely important for returning the heavier elements produced during the life of stars to the interstellar space. This has actually been observed, for example by mapping the composition of supernova remnants. Common elements like carbon, nitrogen and oxygen are produced through stellar nucleosynthesis. Without the planetary nebulae and the supernova explosions, these would remain forever locked in the stellar cores. However, there are still many elements, including most of the iodine, platinum and gold, that cannot be produced through nucleosynthesis in stars or during supernova explosions. These are produced by even more violent events, the merging of neutron stars. As we mentioned, low-mass stars leave behind a white dwarf. However, the remnants of massive stars are more exotic. Stars with mass between 8 and 25 solar masses produce neutron stars. These are objects so dense that they have mass between 1.4 and 3 times the mass of the Sun, within a radius of just about 10 kilometers. A cube a couple of centimeters wide containing material from the surface of neutron star weighs about 3 billion tons. Stars that are more massive than 25 solar masses may leave behind a black hole. The exact mass range of the progenitor that can produce a black hole depends on its composition. Black holes have the most extreme gravitational fields known. Their gravity is so strong that even light cannot escape. They are produced if there is no physical mechanism that can provide enough internal pressure to withstand the gravity of the stellar remnant. This is the case for stellar remnants that are larger than about 3 solar masses.
While white dwarfs and neutron stars can be observed from the electromagnetic radiation they produce, isolated black holes are extremely hard to observe directly because they do not emit any radiation.
Up to this point, we discussed about the structure of individual stars, their energy production and evolution. However, the vast majority of stars is born in pairs or even systems with 3 or more stars in some cases. 2 examples are Sirius and the Polaris stars. Sirius, the brightest star in the night sky, is actually a binary system consisting of a main sequence star that is 2 times more massive than the Sun, and a white dwarf. The two stars complete one revolution around each other every 52 years. The Polaris star is actually a triple system consisting of a binary system with a third more distant companion. If the orbital separation of the two stars in a binary system is small enough so they can exchange mass, we have an interacting binary system. The transfer of mass between the two stars affects the revolution and the orbital parameters of the binary system. For example, as we saw earlier, the more massive of the two stars evolves in shorter timescales. So when it leaves the main sequence to become a supergiant or a giant star, it expands. If the orbital separation is smaller than the Roche lobe of the star, material from this star will start to transfer to its companion. This process often results in the reversal of the mass of the two stars. What was previously the more massive star will now become the less massive one. However, its core will remain massive and it will evolve at a faster timescale than its companion, until it becomes a supernova. The explosion itself will have a very small effect on the system. However, the loss of mass due to the explosion will result in a widening of the orbit of the binary system, or in some cases, it may totally disrupt it. Similarly, asymmetries in the explosion may result in a net velocity imparted on the resulting compact object. This further increases its orbital separation from its companion star. It may make the new orbit eccentric, or it may even destroy the system by shooting the compact object away. After this critical phase, the second star will keep evolving. If the orbital separation of the compact object and the star is small enough, material may flow onto the compact object. As the matter falls into its deep gravitational potential, it will release gravitational energy and it will be heated to X-ray emitting temperatures. These are the X-ray binary systems, one of the most effective ways of discovering and studying the population of compact objects. When the star ends its life, it is very likely we will be left with another compact object. If the system survives this process, we will have a binary system consisting of two compact objects. These are the progenitors of the gravitational wave events produced from the merger of two compact objects. As we see, the survival of interacting binary systems is very difficult. In fact, in addition to the supernova, there are other phases in the evolution of the system that may disrupt the system, or result in the merger of the two objects.
However, the fact that the majority of stars are in binary systems gives a very large parent population. Even if a small fraction of them will have the right parameters to become X-ray binaries or compact object mergers, there are enough systems to observe these very exciting objects and learn more information about stellar evolution and stellar remnants.
On September 14, 2015, we directly observed with LIGO detectors gravitational waves from the merger of two black holes, 30 and 35 times the mass of the Sun. Such a system is expected to be the descendant of a binary stellar system consisting of two very massive low metallicity stars. Subsequently, in August 17, 2017, another gravitational wave event was measured. This time, this event was followed by a short gamma-ray burst 1.74 seconds later. This immediately indicated that the event was the result of a merger of two neutron stars, which was confirmed from the analysis of the gravitational wave signal. Again, these binary neutron star systems are the remnants of binary stellar systems that survived through all the stages of their complex evolution. This discovery was extremely important for two key reasons. It proved that short gamma-ray bursts are produced from the merger of binary neutron star systems, and it showed that the elements that cannot be produced in stars, like iodine, platinum, and gold, are the result of such events. The combined study of individual stellar remnants, X-ray binaries, and gravitational wave detections opens a new window in our understanding of the evolution of single stars and binary systems. Stars do not only exist in binary systems. They're very social, generally forming in groups called star clusters, which contain from a few dozen to hundreds of thousands stars. The stars in a cluster share the same age and chemical composition with very small variations. However, since stars are born over a range of masses which evolve in different timescales, when we observe a star cluster, we will see stars in different evolutionary stages. Stars in the main sequence, giants, white dwarfs, etc.
This is similar to taking a picture of a group of people. We see kids, teenagers, adults, and older people. For this reason, star clusters have been an excellent tool for studying the evolution of stars and testing our models. Star clusters are classified in two broad categories: open clusters and globular clusters.
Open clusters contain very young stars with ages from a few million years up to a few 100 million years. They have between a few dozen to a few thousand members and are generally rather sparse. Because their total mass is not very large, they tend to dissolve. Open clusters trace sites of recent star formation, and they are generally found in irregular galaxies or at the arms of spiral galaxies. Globular clusters are much older and denser than open clusters. They contain several thousand up to hundreds of thousands of stars within a volume of a few parsecs. In fact, in their core, the stellar density can exceed 1,000 stars per cubic parsec. This results in very interesting phenomena, such as interactions between stars, often leading to their merger or their ejection from the cluster. Globular clusters are very old, and stars in them typically have ages older than 8 billion years, making them some of the oldest populations in a galaxy. In contrast to the open clusters that are located close to the site of star formation, globular clusters are often found at the halo of galaxies. The study of open and globular clusters is very important for understanding the different phases of stellar evolution, but also for understanding how galaxies evolve. Stars play a crucial role in the universe. The light of the first stars ended the so-called Dark Ages, when the universe consisted only of cold gas. Stars are the basic component of galaxies. They produce the chemical elements that we see around us and which form planets and the living organisms like us. They are also responsible for several phenomena such as supernova explosions, the formation of impressive nebulae, and some of the most exotic objects in the universe: white dwarfs, neutron stars, and black holes.
Although over the past 100 years we have learned what stars are, how they produce their energy, and how they evolve and die, there are still several open questions. The next generation of ground and space telescopes will allow us to search for the first stars in the universe and answer open questions about stellar evolution, especially the final dramatic stages in the life of stars. This information will bring us one step closer to a more complete understanding of how our universe evolved and formed the galaxies, stars, nebulae, and planets we observe today.